Hi, my name is Jim, and today's topic is motors. There's an awful lot written about them, and in the folder there should be a tutorial on the knowledge series of motors, and they do an excellent job of drawing the windings and the poles and so forth better than I could up here. So this has to do with a simple overview plus the actual model of a motor as it's running without load and it runs with load, and many times textbooks overlook this, and it's important to conceptually understand the way a motor works. Now basically a motor takes electrical energy and converts it into mechanical energy in one form or another, and then that mechanical energy can also be converted. And start with, in general, I've drawn a type of permanent magnet motor, and this would be similar to what would be used in a brushless motor that we see in a lot of drills today, where the armature, or sometimes in an AC motor this is called a rotor, doesn't have any electrical connection to it. It's just a magnet, and if you're using rare earth materials, a very, very powerful magnet. So the way any motor works is through the principle of magnetic attraction and repulsion. Now in this simple little guy here, let's just consider, and I'm actually thinking about making this for fun, if this pole were to be south and this pole were to be north, is that the north would be attracted to the south and it would rotate. I don't have this lined up exactly right, in this direction, and as soon as it gets lined up, this now changes to north and this now changes to south. So the new position of the motor, the armature would be repelled from this pole. Attracted, repelled. Same over here. So in this form of attraction and repulsion is we could get this very, very simple armature to turn. And in a brushless motor there's a whole lot of electronics that sit outside to determine a situation like that. And again, a brushless drill motor would be a good example. So usually in books they start out with an armature winding, and I've elected to use something a little bit different, something that's a little bit easier to draw. Now this is an example of a permanent magnet motor, and in this case the rotor happens to be the permanent magnet. And in many little motors, like in cars and so forth, the permanent magnet is the field. So this would be the armature, and these guys here would be considered the field. So a lot of small PM motors have the field provided by a permanent magnet. Now if we get into the three types of motors, and these are going to be electrically excited fields, so we're not really interested in permanent magnets here. In DC we have the shunt type, and the word shunt kind of means parallel, and in this the winding that produces the magnetic field is in parallel with the armature, and these little red things here are brushes. Those are little pieces of carbon that make connection with segments on the armature which feed current into a winding in the armature, and these brushes are what spark if you have a brushed motor. So this is in parallel with this, hence it's called a shunt regulator, and what's good about it is that it has good speed regulation. Now what that means is you have a no load speed, that's when the motor is just running without being connected to anything, and then as you load the motor down, say connecting, I don't know, a fan to it or a compressor or whatever, is that the speed drops but not a lot. So it's relatively good regulation for a delta load. Also reversing direction is easy. Now it's not just as simple as taking plus and minus and reversing them. It's still turn in the same direction because the current flow relative to the armature and the field would be the same relative to the armature and the field. So to reverse this, what we'd have to do would be cut this winding here, cut this winding here, and actually reverse, say, the shunt winding, and then the motor would turn in the other direction. Now sometimes it's not a good idea to do that, because when motors are made they can take into account certain things like distortion in a magnetic field. So it's usually that a motor is not reversible if it's a quarter horsepower or larger. So that's the shunt motor. And next we have the series motor, and unlike the shunt, the field winding, that would be this guy again, is produced by current that flows actually through the armature. Now what that means is that this current is a lot larger than the current required to excite a shunt field. So a series motor has a heavy winding for providing the external magnetic field because it has to, it's the same current that flows through the armature. Now the advantages of a series connected motor is that it has a large starting torque. And what torque is, a very simple explanation would be if you have a screwdriver and a screw that's stuck and you're twisting on that trying to break it loose. Torque is the ability to twist. You're not doing any work unless you move the screw, but the twisting action is called torque. So it has a large starting torque and it has very poor speed regulation. So if you're dealing with a varying load out here, the speed can be all over the place. Further, it's possible that you'll have a runaway condition, and that basically means that if the motor is unloaded, the RPM, the speed of the motor, will increase and increase and increase until it becomes self-limiting or it self-destructs. And by destruction, I don't mean that it burns up. I mean that it can fly apart, mechanical stuff flying through the air. So there's a danger with series motors if they become unloaded. Reversing is difficult because again you got to go in and change the direction of the winding and so forth. Now there's a compromise called a compound motor, which has the advantages of a shunt motor and the advantages of a series motor. And you have a shunt field here, which typically has lower, smaller current flowing through the shunt windings than through the armature. And also you have a helper circuit with regard to producing the magnetic field, which is the armature current is flowing through another winding, and this is heavy wire, as is this, because it has to carry the armature current. So you get a better starting torque than shunt and better speed regulation than series. Now the one thing that's not shown here is that these magnetic fields have to be aiding. They have to support each other. And if one of these were to be reversed, very strange things can happen to the motor. Overcurrent, it can be running, stop, reverse direction, all kinds of strange things. So when motors are made, there's care given to make sure that the resulting magnetic field of these supports the overall operation of the magnetic field in which the armature is located. So in every case here we have a brushed motor with the little carbon brushes that rest up against what's called a commutator. Now even though the external current is DC, the internal current of the armature is AC. And that's what these brushes are all about, and beyond the scope of our little presentation here. Secondly is, and this is the part that I really want to get across, and this applies to any motor, whether it's DC or AC, but we'll start out with DC. And all I'm going to do is flip the switch here, and when I do that, the motor's not turning at all, and the only thing limiting current basically is the winding resistance and the opposition to current flow caused by an expanding magnetic field in the winding, the L part of the winding, the inductive part of the winding. And there's a time constant associated with this, L over R, which we basically don't care too much about. But if we left the motor in a stalled condition, in other words, if we had the motor shaft so it could not turn, the only thing limiting the current after the effect of the changing current diminished would be the winding of the motor itself, and typically it's not a good thing to have happen. So what happens then is that the current on turn on jumps up, and then it decays and reaches a state above zero, and then as we apply a load to that, it'll increase. Now what's this all about? And let's just consider for a minute that we're dealing with an unloaded motor. The effect of the armature turning in the magnetic field acts like a little dynamo, that is, a generator. and it produces a voltage which opposes the source voltage. So the counter EMF that's produced by the armature turning in the magnetic field is truly what limits the current in the motor. Now, what happens if we load it down? Well, it's going to go slower, the counter EMF goes down, and the current goes up. Now, you may have noticed when your furnace blower motor starts, for example, you might see the lights dim for a second. It's the same deal there, except here we're dealing with AC, and the counter EMF in, say, an induction motor is AC also, that opposes the current flow that's produced by the AC mains. So there are many, many different types of motors, and this model is particularly useful for showing the starting current and the operation current through the generation of this counter EMF. And it's very easy to see, as you load the motor down, you're extracting more energy, electrical energy, or instantaneous power, and that is reflected by just reducing this, which means more current flows. More current flow means more torque, and the product of torque and speed plus some constants is the horsepower of the motor. So that'll do it for this tutorial, and thank you for watching.